Thank you, Joe, for the introduction. So this is the poster for this set of talks over the next 3 days. I'd like you to note the time. It's 2:15, isn't it? Right, good. So I'm starting on time, 2:15. We're all looking at this. What this represents is really the Wheeler delayed choice experiment, or a version of it, a cosmic version of it, whereby photons can be gravitational lensing that's going on, and beams of photons can reach us going either side of this remote galaxy. And the interesting feature of this experiment is that one can choose whether to determine which limb, as it were, of the interferometer, essentially an interferometer, a cosmic interferometer, the photon travelled along, or one can bring the two beams into interference and detect interference phenomenology, which would suggest that we are actually absorbing photons that have, in some sense, travelled both arms of this cosmic journey. Now, the experiment hasn't actually been performed, but I think there's every reason to think that it is going to be performed in due course. And I would like to set it as a challenge, both to myself and my interlocutors, those who champion alternative foundational approaches to quantum theory, to explain this. Okay, but I'm not going to try to explain it today. I will tomorrow. So today my talk is really on many worlds, how they arise, why one has reason to think there are many worlds in the quantum mechanical sense. Tomorrow's talk will be on probability within the many worlds approach. And of course it's only insofar as one has both of those pieces of the jigsaw puzzle in play that one can properly claim to have an understanding of quantum mechanics which is, as I claim, free from ambiguities and conceptual peculiarities. It is challenging, of course. The very concept of many worlds is very challenging, but I claim there is a satisfactory realist interpretation of the theory based on many worlds. I'm going to hold up the Schrodinger equation for you all to see. I think actually everybody has seen it before, so I hope there's no surprises there. The quantum state enters into this fundamental equation, or what looks like a fundamental equation, and as such, for complex systems, it has what I will call a representational role. It represents physical systems. Typically, in many applications, of course, macroscopic systems, but it need not be restricted to microscopic systems. And a part of the point of bringing quantum foundations and interface with cosmology is to pose the question, might quantum mechanics be a fundamental theory that applies unrestrictedly and in principle to the whole universe? So just as electromagnetic field equations, one might think, apply unrestrictedly, or the standard model applies unrestrictedly. Of course, the standard model is quantum theory. What if quantum mechanics applies unrestrictedly? And by mechanics, I mean to include quantum field theory. But part of the, I think, a general good feature of doing conceptual analysis is work with the simplest tools that one can. No simpler, but work with those that one can. So elementary quantum theory, insofar as we can pose and solve conceptual problems within the framework of non-relativistic quantum mechanics, then let us do so. And that works well for many worlds. What's extremely important, of course, is that the method of solution isn't thereby restricted, say, to the non-relativistic regime. Okay, so this is one aspect then to the quantum state. It obeys the equations of motion, the so-called unitary equation. It has a descriptive role. It has another role. It is Janus-faced. It has a second role, which is controlling probabilities for outcomes, experimental outcomes, macroscopic outcomes. And this is an entirely different, entirely separate feature of the quantum state. Okay. All right, so I'm going to discuss both. Of course, I've already said tomorrow will be mostly focusing on probability. Today I'm mostly looking at the representational role of the state. And to that end, I'll start with something rather more modest than than this. I want to consider molecules of Pentacene. It's a polycyclic aromatic hydrocarbon. It's a set of 5 linearly fused benzene rings. It's an organic semiconductor. This is a model provided by chemists, and this model was already available more than 100 years ago, and certainly well before quantum mechanics. But we should take this model seriously, not least because we now have some rather direct experimental confirmation that this is indeed the structure of Pentacene. This is provided from an IBM atomic force microscopic image. IBM Labs. I think this is 2008. There's one more recent in 2011, electron scanning tunneling microscope, where they actually determined the structure of the highest occupied and lowest unoccupied molecular orbitals. So the point about it being an aromatic hydrocarbon, aromaticity is a chemical property that was first defined, really, and analyzed, systematically studied in the 1850s and on. We now understand it in terms of they had a related understanding, and it's a part of my claim that there's great continuity in our understanding of the structure of molecules of this sort. So aromaticity is a property whereby unsaturated bonds or empty orbitals stabilize molecules. It's also a manifestation in quantum mechanical terms of cyclic delocalization and resonance. It was understood in the 1850s and 60s that benzene and other hydrocarbons in a certain class are unusually stable. The structure is distinctive in this way. So what this diagram is showing is double-bonded and single-bonded carbon atoms surrounded by hydrogen atoms, the double lines of the double bonds, the single lines of the single bonds. And indeed, you've really got these sort of 1.5 bonds. The benzene ring itself has perfect symmetry. And what's going on there is, well, let's look at it from a side view. So here's the double bond, here's the single bond. What's going on is these are p electrons that are orthogonal, really, the plane here, this is orthogonal to the plane of the benzene ring. And there's some overlap of the wave function here. This is essential to how these electrons actually couple and how they essentially delocalize. So this is a sort of representation of the electron charge density and how they act to give increased stability to the molecule. So these are so-called pi bonds, also are named after Armstrong inner electrons, inner bonds. Okay. I also said that Pentacene is an organic semiconductor, so it generates excitons on absorption of radiation, electrons excited from the valence band to the conduction band in the familiar way. And what happens then is an electron hole is left behind, and you've got something like, well, it would be positronium if the hole was not screened. The charge is screened, so it's really a hydrogenic atom that's formed, an exotic hydrogenic so-called. And these things allow transport of charge with no actual movement of electrons as such. They also can have parallel and anti-parallel spins and hence fine structure and so forth. Right, so the claim is that we know an awful lot about these molecules. We know a great deal about their structure. And the quantum state is essential in a representational role in this kind of modeling. But let me also add this, that we understand the structure of Pentacene not just as something static, as it were, a snapshot in time, but as a process. It is the unitary evolution which is driving the kinds of coupling involved in giving Pentacene the properties that it has. Okay, so I've got my favorite wave mechanic. I want to just give some more comment on that. This is Michael McIntyre. And what he says here, I think, is absolutely right and really very, very wise here. So in order to understand anything in depth, we usually find we need to think of it both as objects and as dynamic processes and see how it all fits together. I tell my students, what is understanding? Understanding means being able to see something from more than one viewpoint. Make it all consistent, do it all in equations, in words, in pictures, make it all hang together consistently. Richard Feynman often emphasized this kind of thought too. And very often, this is the distinctive thing though that I want to pick up on, we say that's an object, but zoom in and you'll see a process. Okay, so that's McIntyre. He's in the atmospheric physics group in Cambridge. His field is classical wave theory. But in classical wave theory, you also get structures, objects, which have this dual role as a process as well. Okay, so just to return to actually now the benzene ring. So this is a representation made by Jarrett Morse in 1927. And if you notice the scale, 1 angstrom there, that is about right for one of these benzene rings. You see 5 angstroms and so forth. Armstrong's work was in 1890, and of course the structure of benzene was worked out by Kekule in 1865. So what I want to emphasize here is the great continuity that we have through so-called structural chemistry into quantum chemistry and quantum molecular physics. Okay. I've spoken of the representational role of the state. What actually does it say apart from this internal structure? Well, if you just take a single pentacene molecule, of course, I had up its atomic weight, it's a couple of hundred atomic mass units. So it won't stay localized for very long. If you localize it to within an angstrom, it will disperse or cease to be localized pretty quickly, within a matter of a second or two. But that doesn't mean that the internal structure has gone. I remember that relations, relative distances, x1 minus x2, commutes with the total momentum, commutes with the square p squared plus p1 squared plus p2 squared. This is rather important to the original version of the EPR argument. So the structure is maintained, but the center of mass becomes delocalized. But of course, if this thing is embedded in something, some small crystal, perhaps the size of a grain of dust or so, then it will stay localized to within an angstrom for billions of years. As long as the lifetime of the universe, one of these things involved in some small crystalline lattice structure, a matter of a milligram or two, it won't change, it won't move, it'll be there for billions upon billions of years. Okay. All right, so all of that on the representational side of the state. What about the probability side? None of this has been to do with probability. So probabilities, of course, arise typically when one does scattering experiments. One could say when one does any kind of experiment whatsoever, probabilities arise. But let's take a simple example, the Stern-Gerlach experiment. Here you've got, say, electron beam entering a region of an inhomogeneous magnetic field. Depending on its component of spin, whether it has a definite component of spin aligned in one direction or another with relationship to the magnetic field, the electron will traverse the apparatus and arrive at the screen, perhaps at the top part of the screen or at the bottom part of the screen. So we're all very familiar with this sort of thing. And if you get the right component of spin, of course the process will be entirely deterministic in the sense not of which precise bit of the screen does it arrive at, but deterministically it will go to the top part of the screen, say, rather than the bottom part of the screen. Suppose it's spin up. Well, what if it's spin down? Well, then unitarily, deterministically, it will be driven to the bottom half of the screen. Fine. What if it's a superposition of the two? Okay, so it's the superposition of the two states with coefficients alpha and beta. So alpha state of spin up plus beta state of spin down. That's the initial state. Then the thing will do what? If you just apply the unitary evolution, it'll be a unitary superposition of the two outcomes that we previously discussed. And therein lies the problem. Therein is the measurement problem. Probabilities, and the way that this is normally analyzed, probability are introduced at this point to give one outcome rather than the other, depending on the modulus square of the amplitude of the two states involved. Okay, so this is the second role of the state, where the amplitudes are determining probabilities from macroscopic outcomes. All right, so the most familiar and famous example of this, of course, is the Schrodinger cat. So instead now of an electron arriving at a screen, the top part of the screen or the bottom part of the screen, instead you've got a radioactive atom which may decay, nuclear decay, which may then trigger a suitable detector. If the detector is triggered, it breaks a phial of poison. Poison kills the poor cat. Okay, so I think everybody again is familiar with this thought experiment. I hope it's still a thought experiment. It's clear now again that whilst the representational role of the state seems in good order, of course nobody can model something as complex as a cat, but there's no reason to think that the difficulty there is anything more than a technical one. Complex systems will unitarily evolve deterministically in a way that gives a recognizable macroscopic description, a sequence of events, but choose the right or the wrong superposition depending on your point of view, and you will arrive at a superposition of those macroscopic states. The cat here is the example. Probability interpretation of the state is called in to eliminate that superposition so that one or the other is actually realized, a live cat or a dead cat. And a way to sort of think about this is you put the cat in a box, you have an experimenter who, as it were, on opening the box, determines the result, the outcome. Because, of course, the whole point about the second role of the quantum state in determining probabilities of outcomes is just when are those outcomes realized? When does that second role of the state kick in? I'd like actually just to take a quick vote from the audience. I'll tell you a bit of background to this in a minute, but can I just see a show of hands? Who thinks that the cat is alive, X or dead, so exclusive or, who thinks that the cat is alive or dead before you open the box? Can I just see a show of hands? Right, alive or dead. Okay, what about half the audience? Who doesn't know? The other half. Right. So half thinks it's alive or dead. Perhaps a third doesn't know. I won't ask people to put up their hands who think it's not alive, X or dead. But now I want to refine the question a moment. What if the box is very carefully constructed to allow absolutely no possible interaction with the outside world? Can I now see a show of hands who thinks that the cat is alive, X or dead, before you open the box? Still quite... Okay, did anybody change their mind? One person, I see, good, okay. All right, third question, third way of putting it, but I think I know the answer here. What if it's a broom cupboard? A broom cupboard. It's under the sink, it's a cupboard under the sink. Okay, that's where the cat is. Okay, who thinks that... I'm going to rephrase it. Who thinks that the cat is not alive, X or dead, before you open the broom cupboard? Absolutely nobody. Well, that's... Is not alive, X or dead. Exclusive or.
Meaning that it's in a mixed state.
Meaning you don't think the cat is alive, X or dead. I'm trying to keep this really as non-technical question. It has to, I think, really has to be... It's appropriate to answer it as a non-technical question. So nobody puts up their hand. Okay, I'll just tell you a quick story. Oh, one person perhaps. I'll tell you a quick story. So at a conference in... I think I probably better not reveal details. Let me just say, at a conference recently of people, many of whom were working in quantum information theory, one way or another, 80% of the people there put up their hands for believing the cat is not alive, X or dead, even when it's a broom cupboard. Even when it's a broom cupboard. I think that's really salutary, a really salutary thought. Okay. I would put it to you, what if it's not even in the broom cupboard? What if it's just in the tree, in the garden, in the woods? What about then? The thing's still hooked up to the Geiger counter and all the rest of it, nobody around. Now, to then say that there's no fact of the matter whether the cat is alive, X or dead, is, I think, extreme idealism. We should give it its name. It's probably more of an extreme version of idealism than any that I know of any philosopher. Not even Bishop Berkeley thought that whether or not a cat was alive or dead in the woods depended on a human observation, right? Okay, so I'll come back to this question, I think, later, perhaps tomorrow. Anyway, let me just now... we've already been talking about the measurement problem. Let me write it down a bit for you. So it's a set of questions, really. That's what constitutes the measurement problem, or puzzle, or paradox. Why does the collapse of the state happen? When does it happen? To what state does the state collapse? Something happens to the state in the course of measurement. What? Okay. There is, by the way, a third. I mean, I've spoken of a representational function of the state. I've spoken of its probability function as dictating probabilities. There's a third thing that is often in certainly older textbooks, which is the projection postulate, which does tell you how the state changes on measurement. And what it does is it goes to an eigenstate of the quantity that's measured, right, depending on what the outcome is. But that postulate almost certainly isn't obeyed by the great majority of physical systems. But in certain circumstances, it's obeyed, so-called ideal experiments, repeatable experiments. Okay, so one can sort of give an answer to what happens to the state, but it's a very unsatisfactory answer. This collapse process is not subject to theoretical control. It isn't understood, it isn't analyzed, no symmetries appear to be operating. It's the one and only place, of course, where indeterministic goings-on seem to happen, because otherwise one has the unitary evolution. Okay, so very loose set of questions that I think characterize the measurement problem. So what about answers to it? Well, I've given you three kinds of answers. One is the state reflects our knowledge and changes when our knowledge is updated. That's why it's suddenly subject to collapse. Or perhaps the state is incomplete for other reasons. If the state just describes our knowledge, then of course it will be incomplete. It won't tell you everything there is to know about the world. Well, unless you're extraordinarily knowledgeable, I suppose. But anyway, so the state is otherwise incomplete. And here's a third, that there are definite equations controlling state collapse. Okay. So roughly speaking, the first alternative, extremely popular, has had a new lease of life in so-called, well, within the quantum information community. That the state is otherwise incomplete, well, that's the hidden variable approach to the problem of measurement. And the third, definite equations controlling state collapse, that's so-called dynamical collapse theories, of which the Girardi, Rimini, Weber, and Pearl theory is the best known example. And I've pretty well, apart from many worlds of course, exhausted the standard answers to the measurement problem. So on the right I've given some of the immediate difficulties with each of these approaches. And let me go through them in a little more detail. Okay. So Copenhagen is interesting in lots of ways. Of course, it was orthodoxy, insofar as there ever was an orthodoxy. Bohr did persuade or bamboozle, depending on your point of view, a whole generation of physicists to embrace his doctrine of complementarity. It subsequently got to be called the Copenhagen interpretation. That was mostly Heisenberg's work in the 50s. And what makes Bohr interesting is that he had very little interest in the formalism of quantum theory, and indeed articulated the Copenhagen interpretation at a period of time where he understood very little of the formalism of quantum theory. And he said so explicitly. This is his Como lecture of 1927, published in Naturwissenschaften, published in English in Nature, translated into Italian, published in his book, Quantum Theory and Human Knowledge, read by absolutely everybody who was interested in conceptual questions in quantum theory. And there he makes it clear that he is speaking about quantum theory, well aware that many people in the audience understand the theory far better than he. Okay, so this was his explicit statement in the opening pages of this publication, okay, and of his talk. So what does Bohr do? Well, he studies experiments and he uses classical concepts in analyzing them. As such, he doesn't have a measurement problem at all in the conventional sense. But one can address some of these questions here on the right. So, provides no basis for cosmology. Bohr had no trouble at all with cosmology. The cosmos, the universe, is going to be described by classical physics. And there'll be pockets, perhaps, where quantum mechanics kicks in. That's all right. He's going to analyze quantum phenomena too, using classical concepts, but just fragments of classical concepts. This is what gives rise to novelty, according to Bohr. It's not that there are genuinely new quantum mechanical concepts. There are classical concepts, but used in fragmentary ways. No, it does not suggest an alternative and more fundamental theory waiting to be found, as long as Bohr's prescriptions work, of course. Does it make an arbitrary and unmotivated division between micro and macro? Well, here there's some division, I think, in the community. But a case can be made that, no, it's rather where classical theory starts to use only where one has to use only fragments of classical theory, that kicks in where one gets to regimes where the typical actions are comparable to the Planck constant. So nothing arbitrary or unmotivated behind that. And indeed, there's not really a division between micro and macro. There's just fragments of theory or non-fragments, or the whole of classical theory. So what's wrong with Bohr's Copenhagen interpretation? Well, I think the simple answer is it just fails to do justice to the actual practice of physics. It just didn't work. It's not true that you can understand quantum physics using fragments of classical concepts. And in fact, the actual practice of physics is to use the quantum formalism heavily. Okay, and Bohr had very little to say about that. And further, that the general principle of complementarity was supposed to be a sort of meta-principle that applies to lots of other sciences, wherever you get mutually exclusive experimental contexts which exclude certain concepts. Complementarity was supposed to kick in, so in psychology, in biology, and so forth. But that just didn't work out. All right. So here, I've got a couple, I don't know if people know, David Merman is a recent convert to quantum Bayesianism or cubism. So this is, insofar as the quantum information community has a distinctive interpretation, it's this. I won't go into the details. If one looks at this list, I think it fails on every single one. Every single count it fails. Certainly provides no basis for cosmology. I mean, look, I should say something about what is quantum Bayesianism. It's this, that quantum theory is not actually a theory about physics, microsystems at all. It's a high-level theory about information. We have learned that there are fundamental principles about how information can be gathered and processed, which is governed by quantum mechanics, qua general purpose, high-level theory, where measurement postulates, slightly more sophisticated versions of them, are genuine discoveries about how information is to be handled and how to be processed, and just not about, for example, atoms or molecules. So that, I think, fails to do justice to the actual practice of physics. It fails to do justice to the representational role of the state. Makes an arbitrary and unmotivated division between micro and macro. Well, the quantum experiments just are black boxes. It does indeed suggest an alternative and more fundamental theory is to be found, namely whatever does describe the goings-on in atoms and molecules, because it's not quantum mechanics, okay, and provides no basis for cosmology. So I think fails on every single count. So here's Pilotwave Theory. Anthony Valentini will be talking at length about this, both today and tomorrow. And I think the fundamental issue here, certainly it provides a basis for cosmology, no problem there. It does suggest an alternative and more fundamental theory than standard quantum mechanics, but they perhaps can claim, well, we've done that, we've got it. You know, it's an alternative to quantum theory, and we've got that theory now. So not really waiting to be found, it's been found. But on the other hand, there's a bit of a worry about particle physics relativistic phenomenology, whether they really can be handled in pilot wave theory. I hope Anthony will be speaking a bit about that. No arbitrary and unmotivated distinct division between micro and macro. What about the actual practice of physics? Well, here I do have a criticism of Pilotwave theory. It comes back to things like Pentacene. How is Pilotwave theory helping us to understand these sorts of structures? How is knowing the behavior of the corpuscles, the trajectories introduced in Pilotwave theory, how is knowing the details of those trajectories going to help us at this level? So is it really engaging with the actual form of understanding made available in physics? Okay. So here's another well-known theory. I've already mentioned it, the dynamical collapse theory. Again, no problem with cosmology. It provides a basis for cosmology insofar as the theory exists, of course. It does, though, require real progress. It is in no sense a completed theory. In no sense do we have a relativistic dynamical collapse theory. No arbitrary and unmotivated division, no problem there. Now here, with the actual practice of physics, does, I think, rather better, because mostly, as long as you don't have macroscopic systems interacting with the micro, it more or less replicates what we do already in atomic and molecular physics. But of course, there's the problem of particle physics. Okay, so I come on to, well, decoherence theory I'm going to talk about in greater detail in a minute. Let me talk about the relational type, say color. I hope it's all right for me to put you up there. And where does this lie on the spectrum? Well, we perhaps need to get a bit clearer on what the relational interpretation is. That's perhaps less well known than the others, and I'm not an expert, but roughly I think it's this. So if we go back to Schrodinger's cat and it's in the box and we have the experimenter, and what was so unacceptable about this general framework, which is the standard collapse, the measurement postulates, is this arbitrary division. Why can't we apply quantum mechanics to the experimenter as well? But here the brilliant suggestion is you can. Fine. Put the experimenter in a bigger box and have another experimenter perform the experiment on the first experimenter and so forth. So the cat inside the box may be in a superposition of states to the first experimenter. So this chap sees these as in a superposition. Now, this guy could himself be involved in some complex quantum phenomenology such that he would be in a superposition as well. That would be resolved by this guy, and so forth. There's never any way of getting beyond this constraint, really. So, Carlo, I hope I haven't made too much of a mess of that. So if we go back to the list of what's wrong with it, I don't think it fails to do justice to the actual practice of physics, because after all it's representational. It's got all the representational side of it going, and, well, it has the measurement postulates in play. Those are, that is part of the actual practice of physics. It doesn't make an arbitrary and unmotivated division between micro and macro. You can apply it to macroscopic systems if you want. It doesn't suggest an alternative and more fundamental theory. But what about cosmology? I think in this respect, it surely does offer a complete bar on applying quantum mechanics to the universe as a whole. Now, whether that's a serious failing, of course, is part of what this meeting is about. All right, so, but look, I've sort of said it's all right on this score, but I want to come back to this because there is a general practice, if not in physics, if not in quantum mechanics, then everywhere else in science there is a general practice, the actual practice of science, on how to deal with questions of observation and instrumental intervention. So I'm just posed the question here, how in a dynamical, well, I've got physical theory, but I really want scientific theory. Do we analyze a process of observation or the observer of any sort of system at all? And here is what I claim to be universal across all of the sciences, with the possible exception of quantum mechanics. You represent the observation process itself, and if need be, the observer O, as coupled to S or as embedded in S. So any sort of form of what philosophers call naturalized epistemology, whereby one brings science to bear in understanding and learning how observation actually works, how it proceeds, how data is obtained. You embed the system in an environment and you study the two together. Okay, so that is actual practice right across the sciences. Okay, and this is really completely innocuous in almost every context except quantum mechanics. But not entirely. I do want to give you one context in which it does seem to bear in a quite a central way on metaphysical questions. And I want to, in particular, the issue of time, the nature of time. And I'm raising this partly because it's fun, partly because there are relationships between the treatment of time and the treatment of probability, and partly because I think it does illustrate something very important about how the state of how science deals with observation, and also in particular how cosmology does. Okay, so here's a statement of vials. Here I've given a representation of a world line. This is really representing this lecture as it's been going on. So Vial, one of the most philosophical of all of the great generation of scientists who developed quantum theory, said this: "The world is, it does not happen. Only to the gaze of consciousness, crawling up the lifeline of your body, does it fleetingly come to light." And so here's the world line. And I did ask you all to pay attention when I floated the delayed choice experiment, and I pointed out the time. It was 2:15. And I think everybody was awake, weren't you? Well, I hope you were. It's very rude of you if you weren't. I mean, it's one thing to fall asleep during a lecture, but right at the beginning, you know. So anyway, so there's a consciousness. We've got to have some consciousness there because that was the time, and everybody's agreed we were conscious at that point. All right, and there it is. It's gone up to the time now. I'm running a little bit late. Oh dear. But anyway, there it is. So fine, except there's a problem. What happened to the consciousness at 2:15? Okay, so at 2:15 there are all those things going on. Shouldn't there be that consciousness going on there too? Well, we can sort of fix that up. I mean, what we need to do is we've forgotten about the consciousness that was an earlier time that got to there in the time this got to now. That's surely what happened, isn't it? So that's what we need to do. Now, there we've got the consciousness there, and we've got it there, so everything's fine. But, oh dear, of course the trouble is, thing keeps going, and so again we've got a problem, you see. So, well, we sort of can keep going, you know, we can, there's a third one, and, you know, but it is a mug's game, isn't it? And we know really what's got to happen, don't we? We know what's got, because, you know, you've still got the same problem, so really what's got to happen is this. This is what's got to happen. The whole thing is just conscious. You know, unless somebody fell asleep, of course, but anyway, the whole thing is just conscious, right? And this is a very inappropriate way to represent the observer in a temporal setting. I think that's what's going on. Indeed, the observer isn't really being represented, not appropriately. It's being represented with the aid of a meta-time, and that creates nothing but paradox. It's fine to locate oneself on this world line. We're now around about here. It is in the nature of consciousness, and interestingly, fundamentally, that however it is instantiated in physical systems, it seems to occupy something between 10 and 50 milliseconds of that local region of time. So, you know, consciousness localized here is aware of what's going on in around about 10, 50 milliseconds. But here it is too, but a different period of time. Here it is too, a different period of time, and so forth. Consciousness is distributed everywhere here. Okay, so this I've rewritten again the right way to do it. So you need to represent the observer along with the physical systems that the observer is analyzing. Right. So I hope all of that is sort of uncontroversial, although there are many philosophers who take great issue with it, and some physicists, as witnessed Lee Smolin with his recent book, The Rebirth of Time. Okay. So how does this work in quantum mechanics? Well, very clearly, include the observer in the physical system that one's studying. So here I've got, you know, before that's the spin-up state, here's the apparatus state. Now here's the observer. I've got a state representing the observer. And under the unitary evolution, an atom, whatever, the electron is absorbed. We've got a readout from the instrument. The observer hasn't yet read anything or looked or whatever, hasn't interacted with the measuring apparatus, but under the unitary evolution eventually does and sees spin up. So all of that is entirely straightforward. This is the representational function of the state again. Under the unitary deterministic evolution, everything seems to be fine. But of course, the problem is, what if the initial state is the superposition? And then you get a superposition of this form. And one thinks, oh, well, that's the big problem. But of course, if you've been paying attention, you'll realize that we're not here being given anything contrary to our actual perceptual evidence. And the reason is, if you want to model perceptual evidence, if you want to model this process of observation, you want to analyze it, describe the observer in the system. We've just done so, and what that observer is doing is reading the measurement outcome. This observer is reading a different measurement outcome. And of course, this just gives us many worlds. Okay. The observer himself or herself becomes entangled with the system under study, and one arises at a superposition of an observer seeing one experimental outcome, the cat is alive, and the observer seeing another experimental outcome, the cat is dead. And that, of course, was Hugh Everett's central insight into how to understand quantum theory. Why don't we see superpositions, macroscopic superpositions? Answer: when they arise, everything enters into the superposition, including the observer and the environment. So it's absolutely central. Nothing, as it were, can stay outside of this developing superposition. And if we need more evidence that this sort of thinking is absolutely central to physics and always has been, consider how Galileo responded to the question of why don't we see the Earth move. Answer: the Earth and everything on its surface and in its atmosphere are subject to the same motion. Okay, it's essential to model the observer in the system considered. All right, and Everett himself made that parallel. This is in the famous footnote to his 57 paper. This was the only point in the paper where he actually made it clear that he was advancing a theory of many worlds, although he didn't use those words. We know that his supervisor, John Wheeler, insisted on a very drastic editing of his PhD thesis, down to just a few pages, 15 pages or so, which was eventually published. There's a little comment here that in the Copernican case, the addition of Newtonian physics was required to be able to show that the Earth's inhabitants would be unaware of any motion of the Earth. I'm not sure if that's true. I mean, what one needs is the principle of inertia. That's what one needs. One doesn't really need Newtonian physics. But, well, there's something more to say about that. I'm going to say it after noting another aspect to Everett's 1957 paper, which after all was called relative state formulation of quantum mechanics. So this is a summary of a central argument in the paper, and all of it is italicized, the whole paragraph. There does not in general exist anything like a single state for one subsystem of a composite system. Subsystems do not possess states that are independent of the states of the remainder of the system, so that the subsystem states are generally correlated with one another. One can arbitrarily choose a state for one subsystem and be led to the relative state for the remainder. Thus, we are faced with a fundamental relativity of states, which is implied by the formalism of quantum systems. It is meaningless to ask the absolute state of a subsystem. One can only ask the state relative to a given state of the remainder. Okay. And if you think about this, the parallel with Galileo isn't actually so good. If you think about it, the real parallel is with Descartes. It was Descartes who asked, what is motion? And it was Descartes who advanced a fundamental relativity of motion, not Galileo, not anyone before Descartes. What is motion? And of course, one can relate motions of one subsystem to any other subsystem. One's got an enormous multiplicity of relative motions. Which, if any, is somehow preferred, or the true motions? Well, let me pose it in this way. it's all very well for Everett to have a relativity of states, but to be informative, we'd better choose states, the right states, as it were, to inquire relative to those, so as it were, the correct states. What is the situation? Just as with relative motions, it's rather important that you refer motions to the right sort of bodies or frame of reference. And as soon as you put it in those terms, then it's clear that it was really Newton who, as it were, showed how to do physics given the fundamental relativity of motion, how nevertheless to define, characterize those bodies relative to which the equations take a simple and informative form. So, and to do that end, he needed dynamical principles. Now, I think probably you can guess where I'm going to go. How are we going to select the correct relative states, relative to which we have something like observed phenomenology? And the answer to that is it is dynamical in origin, and unlike in Newton's case, the work of many, many physicists over a very long period of time. Some of them not directly working on this problem, most of them in fact, some of them directly working on it. It starts with Ehrenfest. I've got Wigner in there, Wigner distribution, how to represent quantum mechanic evolution as a function, not necessarily probability distribution, because it's not always positive, on phase space. Richard Feynman, I'm thinking of his work with Vernon on the influence functional. The young David Bohm, his 52 paper, and also in the 51 book, arguing that components of the state involving many degrees of freedom, superpositions of such, certainly in the position basis, are going to lead to effective failure of interference effects, no interference effects. Dieter, the first to really focus on decoherence as what is needed in the Everett interpretation in order to give real content to it. Jim Hartle, Murray Gell-Mann, and of course Wojciech Zurek. None of the last three, well, Jim is a sort of interesting case, but certainly not Murray Gell-Mann or in most of his writings anyway, Wojciech, in support of many worlds.
Actually, we had a vote at his birthday conference about whether he was actually a many-worlder in the closet or not.
Uh-huh.
And an overwhelming majority of the participants said yes, he is many worlds, but just refusing to come out of the closet.
Yes.
He just redefined the word exists.
And what did he say to that vote?
He laughed.
Ah. Well, we all have our Wojciech stories. Mine is editing a book to which he contributed a chapter. In the introduction, I was making various comments about his chapter. He was quite keen to find out what I was saying about it, understandably. The power of an editor, my gosh, you can say things about people's chapters. But I wanted to get clear, I wanted to do justice to what he had to say, and this is his bottom line. He wants to be neutral on whether or not there are many worlds. And I can scarcely think of a topic on which one can less be neutral than that one. But anyway, there's some very interesting questions that arise on the role of decoherence theory in Everett, partly because many advocates of Everett, I call them second generation. First generation was just Everett on his own, possibly with John Wheeler. Second generation would be Bryce DeWitt, and I'll include David Deutsch and Lev Weidman. Almost no role at all for decoherence theory. And that's rather interesting. I mean, especially in the case of Weidman and Deutsch, because after all, they were working in the 80s and 90s, long after decoherence theory came to the fore. But the same one can say the same of DeWitt. So how is that? How was it that they, as it were, could get by without it? I want to just say a few words about this. But before, let me go back to the first generation. Let me go back to Hugh Everett himself. Hugh Everett was not so innocent of decoherence ideas as one might think. Here's what he had to say in his long thesis. Any general state can at any instant be analysed into superposition of states, each of which does represent the bodies with fairly well-defined positions and momenta. Each of these states then propagates approximately according to classical laws, so that the general state can be viewed as a superposition of quasi-classical states propagating according to nearly classical trajectories. And what he then did in a footnote was refer to von Neumann's book, and the specific pages there were where von Neumann defined projection operators onto phase space. I mean, he had Gaussians, which he took integrals over a coarse graining of phase space to arrive at projection operators. And von Neumann called these the building blocks of reality. The building blocks of reality. I can't think of a better phrase for them from an Everettian and from a decoherence theory point of view. And of course, what von Neumann knew about and what Everett knew about was Ehrenfest's work. And it was very clear to anyone who gave it a moment's thought that if you've got quantum states, let's take an isolated system, take a quantum state for an isolated system which is well localized in position and momentum, then that state as a whole will evolve quasi-classically. Okay, and that just follows from Ehrenfest's theorem, and it's very quick. Okay, so I think one ought to understand that Everett had some sense of what is the appropriate basis and so forth. But what can't be denied is there were other elements in his work. And if we look at his actual notation, he had this business of the apparatus as a sort of automata with a memory register. Here's the register. And then the thing unitarily evolves so as in the register there is the actual outcome. And this was on the von Neumann model of measurements. And then it follows that when you've got a superposition of these states phi I, here it is, that you get a superposition of the automata, each with the outcome registered. And if it's a repeatable measurement, then you do it again, then you get two outcomes registered, and it's the same outcome. So very centrally, you recover the projection postulate, in other words. And if it's not such, if you've got many copies of the quantum state, you've got a large number of systems, you're doing repeat measurements, then you build up in the register a sequence of outcomes which has a certain statistical structure, and so forth. So that was how Everett was working with probability. As I've said, I'm going to cover probability tomorrow. But the comment to make here is that once you wed the theory closely to a von Neumann theory of measurement, in a way you hardly need decoherence theory. You know that experiments are going to exactly be structured so that microscopic states lead more or less deterministically, choose the right basis, to a macroscopic outcome, and the distinct macroscopic outcomes are not going to interfere. Okay, so you know that already, which I think is partly explaining why people like DeWitt and Deutsch and Weidmann saw no particular need for decoherence theory. But the great need for it, of course, comes as soon as you forget about experiments altogether. Let's just talk about the natural world. Let's talk about the world before there are any human beings around to do experiments. Let's just talk about natural phenomena. One has a quantum state, unitarily evolving. The onus is on the many-worlder to show that that quantum state can be understood as a multiplicity of dynamical processes, each of them evolving approximately classically. So the onus is on the many-worlder to show that, and I think the only way to show that is using decoherence theory, but I think decoherence theory is successful in showing that in a ubiquitous sense, given complex systems, not in too peculiar an environment, so not at absolute zero and so forth, the state will evolve so as to be representable, one way of representing it among others, as a superposition in each of which there's a pattern evolving over time in a quasi-classical way. Okay. And if that's right, I mean, that I think is a straightforward, fairly straightforward anyway, mathematical claim about the formalism of quantum theory. If that's right, then we should take those evolving patterns as real structures. David Wallace has taught me that the person to go to for the clearest writings on these matters is Dan Dennett, and I have certainly come to that point of view. Here's a couple of things he said. Functionalism is the idea that handsome is as handsome does, that matter only matters because of what matter can do. Functionalism in this broader sense is ubiquitous in science and is tantamount to a reigning presumption of all of science. I think that is right. And here's Dennett's criterion. I think the wording is due to David. Yeah. A macro object is a pattern, and the existence of a pattern as a real thing, I suppose, depends on the usefulness, in particular the explanatory power and predictive reliability of theories which admit that pattern in their ontology. Okay, so I'm running out of time, and I'm sorry about not having time for questions, but I just want to make this rather important point, that people often talk about worlds as emergent, or quasi-classicality as emergent in quantum mechanics, or from the quantum state. What is involved in actually deriving that emergent structure to the state involves things like coarse graining, tracing out over degrees of freedom of typically radiation, light particles, focusing on certain more massive systems, considering their effective behavior. Okay, in that way you get this quasi-classical evolution. But it's not emergence. If you call that emergence, it's not emergence in the normal sense. In no way is the quantum state itself approximately modeled by that evolving pattern. What is the claim? The claim is this: it's all of those evolving patterns in a superposition which approximately represents the quantum state. Okay, that's the point. And most emergence isn't like that. Okay, so this is a slightly special way in which classicality emerges. It is the whole multiplicity as emergent which gives you an approximate description of the unitarily evolving state. Okay, so I want to close though just with the three pillars on which I think the Everett interpretation, not putting probability aside, so three pillars. One is, I'm calling it Galileo's directive, represent the observation process itself, and if need be, the observer O is coupled to S or is embedded in S. Dennett's criteria, okay, I've already just read that out. And I come back to McIntyre's principle. In order to understand anything in depth, we usually find we need to think of it both as objects and as dynamic processes. Because the point about these quasi-classical worlds, they really can only be understood as dynamically evolving objects. Okay, you can't just take an instantaneous snapshot of the quantum state and somehow deduce that it's a superposition of worlds. Or along that way, you can represent the state in any way that you like. But it is the dynamic structure of these propagating patterns that marks them out as objects, as part of real physics. Okay, so thank you very much. Tomorrow I'll talk about probability.